Alright, how's it going, Dr. D? I'm going to explain how an X-ray circuit works, how an X-ray tube works, and how it creates X-ray photons. So we're going to start off with the main switch. The main switch is controlled from the control console. You flip that on, it gives life to the X-ray circuit, and it warms up the X-ray tube. We'll get to that in a little bit though. I want to mention that the main switch is supplied with incoming line current from the outside by the power companies. The power companies will supply 220 volts worth of power to our building, but before that, it goes through a transformer, which lowers the voltage from 220 volts to 110 volts, and then it is then supplied to our building. And so we're going to start with the low voltage primary circuit side. This is everything that we control. We control everything on this side of the X-ray circuit. And there are also 3 line currents. 2 of them are going to be going through the kilovoltage side, and then the last one, which is labeled in green, these 2 are labeled in orange. The one that's labeled in green for mass is going to go through the milliamperage side. Anyways, so we're going to start with the kilovoltage side. So you set your technique in the control console, and the kilovolts meter is going to read your KVP, your preset value for your KVP technique. So the auto transformer is the actual KVP selector, so it's like a little dial that selects preset values of KVP to your preset value that you set on the control console. So say you picked like 80 kilovoltage, and the auto transformer is going to select 80 kVp on this little dial. So say these little dots are about 20 kilovoltage peak worth each. And so since you selected 80, it's going to go from 20, 40, 60, 80, and the dial will just go to the kVp that you selected, and that'll complete that circuit. This is also the first electromagnetic induction. So I'm going to go to the exposure switch and the timer. So the exposure switch is actually the final connection that you're going to make in your X-ray circuit, and it's actually the timer goes well with the exposure switch, and of course the the filament ammeter. But the timer is basically the set amount of time that you leave on on your control console, and so the exposure switch, once you say like you put a set amount of time for the exposure switch, and say it's usually like a little alarm, like that visual or audible alarm, like a beeper or like flashing lights indicator, for you to release your finger off the exposure switch, and then for the timer. So yeah, that's for the KVP side. We're going to go down to the milliamperage side. So your timer already has the set amount of time, and then your filament ammeter and your variable resistor are going to take care of the milliamperage. So similar to the kilovolt meter in the auto transformer, the filament ammeter is going to read it's going to read your technique on the control console that you set, and it's going to select the set milliamperage. The variable resistor is going to be your milliamperage selector, and it's going to select the set amount of milliamperage that you selected from the filament ammeter. So that being said, you're going to notice that the line does go all the way around, and it goes over by the auto transformer, but it doesn't connect. The main reason why it doesn't connect is that if it does, it'll confuse the circuit, and then it basically overall won't work. But it does. It is a oh, by the way, this is the second form of induction. This is going to be the third one is over here, and this is going to be the third form of induction. So by establishing conduction, it's going to complete the circuit for this side, but but by not connecting it physically, it won't confuse the circuit, so it can continue its job. But yeah, so establishing that, we're gonna move over to the step-up transformer. The step-up transformer is gonna basically jump the voltage from 110 volts on this side to 10,000 volts on this side. So if you notice how these coils are more tightly packed and drawn together, that means that they can hold, they're more capable of holding more electrons, which will also capable of raising the voltage so high. So it's going to go from 110 volts to 10,000 volts. So this MA meter is going to be the one that measures and ensures that we have 10,000 volts for this side of the step-up transformer. So once we establish that, if it measures to be over 10,000 volts, it's going to go towards this little symbol right here for the ground, and it's going to store the excessive voltage over here. But say you measure it, the MA meter measures it, and it's below 10,000 volts, it's going to stay on this side of the step-up transformer, and then it just won't go through. So anyways, so once you get your 10,000 volts from the MA meter, it's going to be stored in a capacitor. It's not in this diagram, but just should be aware of it. It is then stored in a capacitor. Oh, also, by the way, yeah, fourth form of induction. I forgot if I said that. But anyways, yeah. So the voltage, the 10,000 volts is stored in a capacitor, and it goes through a falling load generator. So this falling load generator will then release the currents in a drop-like pattern, and like it's more like a concentrated drop-like pattern, like pulsating drop-like pattern. So it's like very concentrated set amounts of volts that is produced. And so after the falling load generator, it's going to go to the 4-diode rectification unit, or the rectifiers, and it's basically the rectifiers change it from alternating current to direct pulsating currents, which is extremely way more efficient for X-ray tubes, for X-rays. And so there is also 2 types of pathways for the high voltage secondary for the rectifier circuit line current pathways. It's going to be, so the first one is drawn on here with a blue highlighter. So you're going to start over here. So right, down, down, right, up, left, down, down, left. So that's one pathway. And then you're going to have the other one. It's going to be right, up, down, right, up, left, down, up, left. So I just want to take a minute to compare it real quick. If you notice that they are always going to be parallel to each other. The pathways are always parallel. So yeah, I just want to establish that. Anyways, so I also want to get to the step down transformer. Now this is very important because since we have 10,000 volts being supplied to the X-ray tube on the anode side, which will then again be supplied to spin the stator, but here we go. There we go. So yeah, so very similar to the step-up transformer, since there are less coils on this side, it's going to hold less electrons and is capable of holding less electrons. So it's going to bring, so since we can't bring 110 volts to our filaments of the X-ray tube, it's going to bring it down to say like 10 volts or 3 to 5 amperes. So it's going to bring it from 110 volts to like 3 to 5 amperes, and it's going to bring it towards the filaments of the X-ray tube. Now, that's also, also, yeah, it's the 5th induction. All right, so having said that, now we move on to the X-ray tube. So the 10,000 volts is then supplied to the stator electromagnets. This is a lot of voltage supplied to very powerful magnets. So these powerful magnets will then create an electromagnetic field around the rotor, which then again is which then creates an extremely powerful magnet, and will then spin the rotor at a very great speed, which is what we need for it to turn the anode disk. Of course, the ball bearings are going to keep it in place, keep it so it runs smoothly and efficiently. And the tungsten anode is basically the anode's made out of tungsten for various reasons, mainly for having a high atomic number, high melting point over 3,000 degrees, and so on and so forth. But yeah, basically the tungsten is the ideal because it's perfect for holding a lot of electrons and high heat conduction, and it's pretty much the perfect element. But anyways, so we're going to go to the filament circuits. The filament circuit is then supplied from the step-down transformer side, and this is the side that gets 3 to 5 amps supplied to it. So it is then supplied to the cathode side, the negative side, which is also near the filament's going to be over here. So it's going to go towards, yeah, it's filament right there. So it also has this little cup-like thing right here. If you can see right there. This little cup-like figure is actually called the focusing cup. The focusing cup is made out of nickel, and the point of the focusing cup is it's supposed to narrow the thermionic emission, and it's supposed to focus it in like a more narrower, straighter, efficient stream towards the anode. So this is basically where X-ray photons are produced. Since the focusing cup narrows the thermionic emission and produces a thermionic cloud towards the tungsten anode, it's going to create X-ray photons. But that being said, it's not all, even though that this will create X-ray photons, not all the photons created are going to be efficient. Of course, in the envelope, if it'll create X-ray photons, but some may bounce off and hit the envelope, or it won't always go towards outside of the X-ray tube. It's efficient, but not 100% efficient, so it's not perfect. But basically, as the 10,000 volts are supplied to the stator electromagnets, it'll then move the rotor, and it'll then rotate the tungsten anode very, very powerfully, and then the filaments going to be then supplies the is then supplied with the focusing cup, and the focusing cup narrows the thermionic emission cloud, and basically this is where X-ray photons are produced. And I think that's it. Yeah, I think that's it. All right, so 13 minutes. I'm so sorry if that took longer than it needed to, but thank you for your time, and I hope to see you soon. All right, bye.